Daily Section, January 8, 2026. ET, Ambient Energy Manual Title. Field First Engineering. Lost, Electrotechnics, Proven Equations, and How to Test the Fringe Version. V0.9 Purpose of this section. This section is a toolbox for designing and falsifying ambient energy and anomalous power claims with classical physics that still works, components that still exist, measurement discipline that survives controversy. It is written for builders who want devices that last decades, no upgrade cycle, and for investigators who want to separate A. Real harvesting, storage, B. Hidden energy inputs, and C. Honest mistakes. Scope: atmospheric electrostatics, impulse, high dV, DT systems, single wire, return path tricks, saturable core magnetic amplifiers, and the minimum instrumentation protocol set for defensible claims. First principles. Design with fields, not fairy dust. 1.1 Start with conserved quantities. Everything we do must close an accounting loop. Energy. Do, dt equals pin minus pout minus plus. Charge continuity. Nabla J equals minus sign partial differential rho, partial differential T. Maxwell. Fields are the storage and transfer medium. Electrons are one carrier among several. Most mystery generators are I. Energy storage plus timing, E. Impedance transformation, E. Parasitic coupling to a big reservoir, mains, ground, RF, thermal, or IV, measurement artifact. Your design and your test plan must explicitly rule out EIV. 1.2 The 5 reservoirs you can legally and repeatably tap. A. Thermal gradients, TEGs, TPV, radiative cooling, heat sinks, B. Mechanical vibration, strain, piezo, TENG, magnetostrictive, C. RF, EM, rectennas, near-field scavenging, NFC, UHF, 5G leakage, D. Chemical, batteries, corrosion cells, galvanic, soil potentials, E. Electrostatic, atmospheric, electric field gradient, precipitation charging, wind-blown charge, corona. Everything else, LENR, radiant energy, vacuum energy, must be treated as hypothesis under test until a calorimetry and controls package survives replication. Atmospheric electricity. What the environment really offers. 2.1 Baseline field and why it matters. In fair weather, the near-ground atmospheric electric field, potential gradient, is typically on the order of approximately 100 V per meter, often quoted around approximately 130 V per meter. This means a 10 meters height difference can be approximately 1 kilovolt of potential difference, but at extremely low available current unless you have precipitation, sharp points, or large collecting area. Design implication. Atmospheric collectors are usually best for sensing, timing, intermittent low power loads, charging small caps, supercapacitors slowly, bias supplies, E-field meters, ion counters, not continuous kilowatt power. 2.2 A conservative collector model your elevated electrode plus downlead as coal to infinite atmosphere, leakage R leak to air, insulators, a nonlinear current source from corona, ion collection when E exceeds threshold at sharp points, a return path to ground that is never ideal, soil has resistance, capacitance, and electrochemical potentials. Key equations, starter set. Capacitance to ground, order of magnitude, C approximately equals 2 pi 0 L, lane, 2 H, R, for a vertical wire of length L at height H, radius R, rough approximation, treat as a design estimate. Energy stored in a capacitor, U equals 1/2 CV squared. Reality check. Even 100 picofarads at 10 kilovolts is only 5 millijoules. 2.3 Engineering rules for Tesla-style, radiant, atmospheric collectors, safe, testable version. Rule A. Separate, collector, storage, and load, collector. Geometry plus insulation plus corona control storage. Caps, supercaps, or isolated battery charger stage load. DC, DC with defined brownout behavior. Rule B. Treat insulation as a component, not an afterthought. Surface leakage dominates. Used. Long creepage distances, smooth surfaces, avoid grime traps, hydrophobic coatings where appropriate, guarded insulators, Faraday guard rings, on ultra-high impedance nodes. Rule C. Put the physics in the schematic. Every node gets an estimate. Capacitance to everything nearby. Leakage resistance. Expected E field. Expected corona onset. If you can't annotate it, you're not controlling it. Rule D. Ground is not a magic sink for measurements. Use a known Earth electrode system and document. Rod type, depth, soil moisture, resistance to Earth. Use a proper tester. Bonding topology. Single point versus mesh. Impulse systems, spark gaps, and non-Hertzian confusion, without the mysticism. 3.1 What impulse electricity really is, in modern terms. A spark gap discharge produces fast rise time, high dV, dt, high d, dt, broadband RF, strong near-field coupling, non-linear conduction paths, plasma, and spectacular opportunities for measurement error. Many mystery effects are simply poor bandwidth instruments, aliasing in oscilloscopes, hidden conduction paths, or energy coming from the charging supply you forgot to measure correctly. 3.2 Practical equations you can use. Transmission line step response. When rise time TR is comparable to 2-line underscore delay, treat leads as transmission lines. Approximate characteristic impedance, coax, Z0 approximately equals 60 square root epsilon r, lane, B, A. Inductor energy. U equals 1/2 Li squared, magnetic field energy density. UB equals B squared, 2 mu, electric field energy density. UE equals 1/2 epsilon E squared. If you claim extra energy, you must show these integrals and the control experiments, not just brighter bulbs. Magnetic amplifiers, saturable reactors. The lost control tech that's still useful. 4.1 What they are. A magnetic amplifier uses a saturable core and windings to control an AC power path using a small DC control current. It's a power modulator, not a free energy source, but it can survive harsh EMI, tolerate radiation, operate at high temps, and be repairable with basic materials. 4.2 The core idea, in one page. Use the BH curve, core magnetization, H proportional to ampere turns, Ni, over magnetic path length. B rises with H until saturation. Saturation collapses incremental permeability, mu, reducing inductance. Flux. Phi equals BA core induced voltage. V equals ND phi, dt inductance, rough, L approximately equals N squared, reluctance, with reluctance R approximately equals Lm, mu A. A saturable reactor in series with an AC load behaves like a variable inductor whose impedance X underscore L equals omega L collapses as the core saturates. DC control shifts the operating point, so the AC swing hits saturation sooner or later, changing effective impedance, and thus load power. 4.3 Why these matters for our projects. Rugged regulation for harsh grid and off-grid microgrids, especially where semiconductors are a maintenance liability. Soft start and current limiting for experimental harvesters, TEG stacks, piezo arrays, TPV converters. Century design, control elements, cores plus copper plus insulation, that can be locally manufactured. Measurement discipline. The minimum standard for high ambiguity energy experiments. 5.1 Non-negotiables. A. Define all boundaries. Draw a box around your device. Every wire, pipe, shaft, antenna, and ground bond crossing the boundary is an input-output channel that must be measured or ruled out. B. Measure input and output with bandwidth and phase awareness for AC impulse systems. True power is P, T, equals versus T, I, T, and average P is VI, with correct timing and bandwidth. VRMs times ERMs is wrong when waveforms are non-sinusoidal or out of phase. C. Use redundant methods: electrical, precision shunts plus differential probes plus power analyzer. Thermal, calorimetry. C. 5.3, mechanical, torque times angular speed with calibrated sensors. D. Control for hidden sources, battery swap control, blind labels, Faraday enclosure, RF survey, thermal soak controls, ground isolation controls, open load, and dummy load. Runs 5.2 instrumentation checklist, practical lab tier. True power analyzer, wideband if impulses, oscilloscope with known bandwidth, differential probes, current probe or shunt, precision shunt resistors, 4-wire Kelvin, thermal camera plus contact thermometry, RTDs, thermocouples, and data logger, environmental, temp, humidity, pressure, E-field meter if doing atmospheric collection, RF spectrum analyzer or SDR for it's picking up RF checks, ground resistance tester. 5.3 calorimetry quick start for excess heat claims. If someone claims anomalous heat, the safest path is calorimetry. Option 1, flow calorimetry, water or oil. Thermal equals MCP delta T plus corrections for heat loss and sensor calibration. Option 2, isoparabolic, sealed plus known thermal resistance, calibrate with known heaters, fit time constants, compare runs. Rules: calibrate with known electrical heaters at multiple powers. Report uncertainty and drift. Show raw data, not just processed graphs. Lost, but real. Practical appendix of equations and rules, builder-friendly. 6.1 Electrostatics and amp. Insulation, E equals V, D, parallel plate approximation. Creepage distance design. Treat contamination as conductive, increase creepage and add barriers. Corona onset depends on curvature radius. Sharp points increase local E. 6.2 Resonance and amp. Energy exchange, not creation. F0 equals 1, 2 pi square root, LC, Q equals omega 0. Energy stored, power lost. High Q means low loss, not infinite power. 6.3 Ground, return path surprises. Earth returns and single-wire demonstrations often work because the return path is capacitive, radiative, or via Earth conductivity. Treat it as a two-conductor system where the second conductor is distributed environment. What's worth folding in right now? State-of-the-art notes. TENGs. Current, deployable, trend is durability plus packaging plus charge management circuits, and hybrid TENG plus piezo for real sensor networks. TPV. Selective emitters, spectral control plus thermal management remain the big levers. Record class work is often tied to high temperature sources and optical engineering. Photovoltaics. Most credible near-term value is ultra-long-life microwatt systems paired with supercaps plus duty-cycled electronics. The gating issues are licensing, shielding, and supply chain. Actionable next experiments, safe plus falsifiable. A. Atmospheric collector demonstrator, instrumentation first. Build. Elevated plate or wire, guarded insulator, downlead to ultra-high impedance measurement, storage cap, and a defined load, e.g., intermittent LED flasher. Measure. Field, leakage, charge rate versus weather. Goal. Publish a real power budget versus environment chart. B. Magnetic amplifier, Century regulator, breadboard, build. Small saturable reactor controlling AC into a resistive load. Use DC control to modulate. Measure. Waveforms, efficiency, thermal rise, characterize modulation range. Goal. Produce a design recipe for rugged, low parts count regulation. C. Calorimetry rig template. Build. A standardized flow calorimeter box with calibration heater ports. Goal. Every future, excess heat, claim runs through the same rig. End of section. SHA 256, UTF-8, A2B45D97A7C31F 8047152 C1FDC 95C0E7CB20171D8B8A 335 FBO8F 89C 295520DD. What looks especially actionable right now? Deployable Tang piezo systems. The boring work, packaging plus power management plus lifetime testing, is where real products happen. Consider a manual insert, from lab demo to field node. TPV. If we treat TPV as a high-grade heat to electric module, waste heat, burners, industrial, the design story becomes concrete. Emitter selection, filter, view factor, cooling, and realistic system efficiency. Magnetic amplifiers. Great Century hardware. Chapter insert. A control technology that feels like Tesla-era engineering but can regulate modern low-voltage systems through transformers and rectification stages. Global Robotics Corporation.